Hello everyone. Today we are going to discuss the problem Labyrinth from CSES Problem Set. So let's go through the problem. You are given a map of a labyrinth and your task is to find a path from start to end. You can walk left, right, up and down. So the input contains two integers n and m, the height and width of the map, and then there are n lines of m characters describing the labyrinth. So each character is either a floor, which is denoted by a dot, a wall, which is denoted by a hashtag, a that denotes the start, or it can be b that denotes the end. And it's mentioned that there is exactly one a and one b, that is there is exactly one starting point and one ending point. What you need to print? You need to print yes if there is a path and no if there is no path. And if there is a path, you need to print the length of the shortest such path and its description as a string consisting of characters L that is left, R that is right, U that is up and D that is down. And you can print any valid solution. That is, if let's suppose there are two paths of same length, you can print any of the path. The constraints given is n and m is of the order of 10 power 3. And yeah, this is the input, this is the output. So let's first of all understand what the question is, and then we will see how we can solve this. Okay. So I have taken this input example, the same that was given in the problem statement. So let's see how you are getting this particular output in this question. So as you see, the starting point is A and the ending point is B, right? So looking at this example, you can clearly see that there are two possible paths. Either you go like this is one of the possible paths, or you go like this. This is the other possible path, right? You have only two possible paths in this particular example. Now just let's calculate the length of every path. Let's suppose we say this is path 1. Okay. So let's calculate the length. You start from A, right? You move over here. The length becomes 1, 2, 3, 4, 5, 6, 7, 8 and 9. So if you are following this particular path, the length that you are getting is nothing but 9, right? Agree? Okay. Let's follow the different path. Let's suppose we follow this path. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if you are following this particular path, then the length that you are getting is 11, right? Agree? Now, since we need to choose the shortest path, so definitely the path that we are going to choose for this particular example is this one. So the first thing that we will print is that yes, the path definitely exists. Then we need to print the shortest path, the length of the shortest path, that is 9. And then we also need to print that what are the directions we need to follow to reach from start till the end. So let's see what are the direction we are following. First of all, we are moving left, then we are moving down, down, then we are moving right, 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 and then we are moving up, right? So the path that we are going to print is, first we are moving left, then we are moving down, down, then we are moving right, 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 and then we are moving up. So if you just compare this with the answer given in the output, it exactly matches, right? So this is what the problem statement is. You first of all need to see that whether the path exists or not. This is the first thing that you need to see. If it does not exist, simply print no and back out. If it exists, print the length of the shortest path and also print the directions you need to follow from start till the end to cover that particular path. I hope the problem statement is clear to each and every one of you. Okay. Now, the constraints given in the problem, that is the height and width of this map, n and m, is of the order of 10 power 3. So if you are writing any solution that is working in big O of n square, by n square I also mean you can write it as big O of nm, or anything that's working in big O of n square log n, something like this, will definitely pass. But if you have a solution that is working in big O of n cube or big O of n power 4, this will give you TLE, right? So you have to think of a solution that you can solve within these time constraints. I hope this thing is clear. Okay. So to solve this problem, I will just simply break this problem into two parts. So we are going to solve it into two checkpoints. So the checkpoint one is, first of all, we are going to calculate the shortest distance, and then checkpoint 2 is we are going to calculate or print the path. Okay, so these both are independent problems, and to solve this one you have to solve the first one. So first we are going to solve the first one, and then by taking reference from that we are going to solve the second one. The second one is actually a very important concept, what we say as answer construction. You will see this manywhere in problems, especially in problems of DP and all. You will see this. This is very common. Answer construction. It is actually a skill that you have to develop while coding. So we will see how we are actually going to construct our answer in this case. But let's first focus on this, how we can calculate the shortest distance. Okay. Cool. So how we can do this? Now just see one thing. To understand this better, let me just do one thing. Let me just remove this as hashtag and keep dot over here. Okay, cool. Now just tell me one thing. You are initially standing over here, right? From here you have four possible directions. Either you move up, right, down, or left. Definitely you won't be able to move up and down because there are walls there. So you can either move left or you can either move right, isn't it? Okay. Let's suppose you moved towards right. Okay. You moved over here and then you moved over here. And now currently you are standing over here. So can you say me how much distance you covered to reach till this point? You covered a distance of 2 to reach this till this point, right? Cool. What if you would have started from here and then you have covered path something like this? If you would have done something like this, how much distance it would have taken you? 1, 2, 3, 4, 5, 6, 7, 8. 8, right? You would have reached to this point from this starting point by covering 8 steps. Okay. Why I am saying this? The reason behind is, if you are standing at this particular cell, now once you reach this cell, now again you will have directions to explore, right? You can, from this particular cell, you still haven't reached till the end point. So you can either move over here, or you can either move over here, or you can either move over here, or you can either move over here from this particular cell. Now let's suppose you first reach to this particular cell by covering 2 steps and you explored all the directions from here. Okay. And now while covering this path, you reached this cell again by covering a distance of 8. Should you, now my question is, should you again cover all 4 directions from this particular cell? This is what my question is. Should you again cover all possible paths from this particular cell? Should you? Tell me. No, right? Because you earlier reached this cell by covering 2 steps. Now whatever cells you cover from this particular cell, let's suppose you move to immediate right, you will reach over here in 3 steps. But if you were covering this particular path, you would have reached to this particular cell by covering 8 steps, and moving to that immediate right would have taken you 9 steps. 9th step would have taken you to this particular cell, which was reachable in only 3 steps. So you won't cover, or you won't again start your traversal from this particular cell. So this is the logic that we are going to use to solve this problem, that if we have visited a cell at a distance lesser than what we are visiting it right now, like let's suppose we were covering this path, we reached to this particular cell at distance 8, but earlier we have already covered this cell by at distance 2. then we won't traverse from this cell in any direction. We will simply stop. We will say that I have already covered directions from this particular cell at lesser distance than what it will take me now, so I will not do it again. So this is how, if you follow this thing, you can calculate the shortest distance to reach any cell from this particular cell. So what you can do is, you can do a simple BFS traversal. You can start from this particular cell, maintain something like a distance vector. You can maintain a distance vector that will tell you that to reach a particular row and a particular column, how much steps you took from the starting cell. This is what the distance vector will store. And this is how, at the end, once you have completed your BFS traversal, you can simply see that for the end cell, is the distance vector not very big? Like, we will initialize our distance vector with a very big value. So we will simply see that is the distance vector value not very big. If it is not so, then we will say that, okay, this end point is reachable and this is the distance. So this is how we are actually going to calculate the shortest path. Let us see the code for that, and then we will see how we can actually print the path as well. Okay, cool. So first of all, what I have done is I have taken the input for N and M. Then I have taken the input for maze. So vector string maze, there are n rows and every row contains a string of size m. This is how the input looks like. Then I have taken 4 variables R, C, R1 and C1. So R and C basically denotes the starting cell coordinates and R1 and C1 denotes the ending cell coordinates. So what I am doing, I am simply traversing over the entire maze. If the value of a particular cell is A, initializing it to the coordinates of starting row and column. If it's B, initializing the coordinates of ending cell. Then I have constructed a distance vector of size n cross m. So distance of I comma j tells me that from the starting cell to reach the cell I comma j, what is the distance required. So initially I have initialized it with a very big value, that is 1e9, and later we will change this. Now since we are starting from the cell R comma C, this is the starting coordinate, right? So can I say that to reach to that particular cell R comma C, the distance is 0? Because that is only the starting point, right? So this is what I have done. I have initialized distance of R comma C with 0. Then I have constructed a queue that contains 2 values. So basically pair of int comma int, that is R comma C. Okay. This is the isValid function that will come into use afterwards. So in my queue, since I am at the R comma C cell in the start, so in the queue I have simply pushed R comma C. Now while the queue is not empty, so I am simply doing a BFS traversal. Take row comma column as pq.front and simply delete the front element. Now what I do, I simply traverse over the 4 directions. This is a very common technique as discussed earlier as well, to traverse over all 4 directions, where we are constructing x direction vector and y direction vector. So traversing over all the 4 directions, what will be the value of new row? The current row plus dx of I. What will be the value of new column? Current column plus dy of I. So what is the first thing that we will check? That whether the new row or new column exists or not, right? So for that we have constructed a isValid function passing to which we are passing new row and new column. So let's see this function. So this function is a Boolean function that returns true only if the value of row is greater than equals to 0, column is greater than equals to 0, row value is lesser than n and column value is lesser than n, and also the maze value is not a hashtag. If it is a hashtag, then we won't be able to traverse to that particular cell, right? Because that is a wall. So we will traverse from that particular cell only if all of these conditions are true. Okay. Now if this is not true, we are simply continuing and moving on to the next traversal direction. If it is true, then when we will start traversal from that particular cell, as discussed before, if we have reached to the cell and that is the minimum number of steps required to reach to that particular cell, we will start traversal from that cell. So first we will see that what is the current value of the distance, current value in the distance vector for new row and new column. If that value is greater, then the value it will take us to reach to that particular new row and new column. Let's suppose we were standing over here initially. So standing over here, it would have taken us one step to go from A to this particular cell, right? Now to reach to this particular cell, what will be the distance? The distance to reach this particular cell plus 1, right? The distance to reach this particular cell plus 1 will be the distance to reach this particular cell. This is what we have done over here. So we are simply checking to reach this new row and new column. What is the distance that, what is the number of steps we will take? The current row column distance plus 1. If this value is lesser than what the current value in this distance vector for new row and new column is, then we know that, okay, we have to traverse from this particular cell. So what we have done, we have simply populated the distance vector for this new row and new column as distance of row comma column plus 1, and in our queue we have simply pushed back new row and new column. Once we are done with this, once we are done with entire queue traversal, we will simply see that for the end cell the coordinates were r1 and c1, right? We have already populated that r1 and c1. So if the distance is still 1e9, the value that we initialized with, this means that that particular cell is not reachable, and hence we simply printed no and return. But if it is reachable, we are simply printing yes and also the distance, which will actually be the minimum distance to reach to this particular cell r1 comma c1. I hope this thing is very much clear, that how we are seeing whether a cell is reachable or not, and if reachable, what is the shortest distance. So the first part of the problem, that is the checkpoint 1, is done. Now is the checkpoint 2, that is we need to also print the shortest path, right? Okay, how we can do this? So to print the shortest path, give me a minute. Okay. There can be multiple ways via which this printing the path can be done. There can be multiple ways via which you can code it. I am going to discuss one possible way. One thing is, if I am coming to a cell from this particular cell, let's suppose from this particular cell I came to this particular cell, and it took me 2 steps to reach this particular cell, and initially to reach this particular cell the distance was, let's suppose, 1e9. So definitely from this you will start your traversal. This value is lesser than what the initial value was. So you will start your traversal from this particular cell and go in all 4 possible directions, right? So can I say that to reach this particular cell, you came from the cell that was towards the left? I repeat, to reach to this particular cell, can I say I came to a cell that was present towards the left? So can I say that parent of this particular cell is situated towards the left? Can I say this? Okay, one more time. If I say you, I came to this particular cell in 8 steps. But earlier, you already reached this particular cell in 2 steps. Now tell me, will you update the parent of this particular cell? Will you update the parent? No, right? Because the actual parent of this particular cell via which you were able to reach by 2 steps is situated towards the left. Now, why maintaining parent helps? Just see. Why maintaining parent helps? The reason is, let's suppose you covered these directions. You first of all went here, then here, then here, and then here. If you understand this thing, the entire question will be solved. Okay. So initially, first of all, you covered from here to here. So can I say the parent for this particular cell is situated towards the left? So let's write it. The parent for this is situated towards the left. Then from this cell, you came down. So can I say parent for this particular cell is situated upwards? So I will write the parent of this as upward. Okay. Then from this cell you went over here. So can I say the parent for this cell is situated towards the left? So again, the parent for this I populate it as left. And from here you went over here. So can I say parent for this cell is situated downwards? So I will simply populate its parent as downward. Okay. This was the starting cell. This is from where you started. Now how will you write the answer? If I tell you that, okay, this is the end cell, you already have the parent. Now give the answer for me. How will you do it? See, you will say that, okay, I am standing over here. I know the coordinates of this particular cell, right? R comma C. I know the coordinates of this particular cell. And you also know that parent of this particular cell is downwards. So what you will do? Let's suppose you have some answer vector. In that answer vector, you first of all push down. Okay. And you change your coordinates R comma C according to whatever direction was there. Over here it was down, right? So you will change your R to R plus 1 and C will remain the same. That is, you simply move to the cell that is downwards. Okay. Cool. Now from this particular cell you are moving left, right? From this particular cell you are moving left. So in your answer vector you will simply push left and you will change your coordinates according to that. So your row will remain the same, column will become -1, right? Now from this cell you are moving up, so you will simply push up and you will change your coordinates accordingly. So your R will remain as R and C will remain as C minus 1. And then from this cell you are moving left. So answer vector you will push left and you will change your coordinates as R minus 1 and C minus. You will change your coordinates as R and C minus 2. And you already know the coordinates of starting cell, right? So you will keep on moving to the parent until you reach to the coordinate that matches your starting cell. Let's suppose the coordinates of starting cell were row comma column. So you will keep on doing until you don't get R as equals to row and column as equals to column, C as equals to column. Until you don't get this thing, you will keep on moving to the parent. Now just see what you want. The thing that we have printed right now is actually from end till start. This will give you the direction from end till the start, right? But what do we want to print? We want to print the path from the start till the end. So the first thing that we need to do is we need to reverse this answer vector. So we will reverse this answer vector. It will become LULD. And we also need to change the value of L to R or R to L, vice versa, and up to down and down to up. So L will change to R, up will change to down, L will change to R, and down will change to up. Why we are changing the direction? Because how we have written the direction? We have written direction like this, right? From this cell, we were moving to this cell. So direction written was left. But we need the direction from start till the end. So from this cell, actually, we are moving to this cell, right? So this L will change to R. Similarly, from this cell, we are moving to this cell. So this up will change to down. From this cell, we are moving to this cell. So this left will change to R. And from this cell, we are moving to this cell. So this down will change to up. So this is how actually you can print the path by maintaining the parent. And this is how actually we are going to solve the problem. Let's see the code for this. You will understand it better. Okay, just give me a minute. Okay, so what I made a 2D direction vector n cross m and initially kept all the characters as dot. Okay, now if we are moving to a new row and new column from a particular row and column, so we will see what direction we are following. If the value of I is 0, this means we follow this direction 0, 1. What does this direction means? This direction means that you moved 0 towards row and 1 towards column. This means you move towards right. If you are at R comma C and this is R comma C plus 1, this is what our new row and new column is, right? So this means you traverse towards right. So can I say that for this particular cell, the parent exists towards the left, right? So this is what we will do. If the value of I is 0, the direction of new row and new column, or basically the parent of new row and new column, exists towards the left. Similarly, for I equals to 1, it will be R. For I equals to 2, it will be up. And for I is equals to 3, it will be D. You can see for every I by following this direction vector. Once you have done this, and once you are sure that you are getting a path, what you will do, first of all, I construct this answer vector. I start from the end cell. I already know the coordinates of end cell, right? It is R1 and C1. So I start from the end cell. And while the row does not become equals to R and column does not become equals to C, this R and C were the coordinates of starting cell. So while my row and column does not exactly matches to the starting cell coordinate, I will keep on moving on to the parent. So in my answer vector, I am pushing the directions of current row and column. And according to the directions L, R, U or D, I am changing the value of column and row. As we decided, right? That if we are standing over here with coordinates R, C, if we are moving down, the value of R will become +1 and column will remain as same. So we will keep on changing our coordinates R, C until we reach to the starting coordinates. This is what we are doing over here. In our answer vector, we are pushing the direction of parent, and according to the direction, we are changing our coordinates until we reach to the starting cell. Once we have reached to the starting cell, now we have the path from the end till the start. But what do we want? We want the path from start till the end, right? So first of all, we have reversed our answer. And for printing the answer, what we are doing? If the value is L, we are printing R. If it's R, we are printing L. If it's up, we are printing down. And if it is down, that will come in else, we are printing up. And this is how we have constructed our path. So this is actually a very beautiful problem and very good for the ones, very good understanding for people who actually don't know how answer construction works. This is a very basic example of how you can actually construct the answers in questions like this. And it is very, very important. So it is a very good concept to learn. So in this particular problem, we have learned two things. The first thing was we learned how to get the shortest path. And how we did that? We just kept the distance for every cell, and we were not traversing from that particular cell if we have reached to that cell at a distance greater than what actually we have earlier reached to it, right? And then we have seen how we are constructing the answer, that is answer construction. And in this case, how we did that? By maintaining parent. The most important thing that you have to keep in mind while maintaining parent is you are updating parent when we are actually reaching to that particular cell from the initial cell, right? At that time only you are updating the parent. So this is actually the correct parent, right? Why I'm saying this? If you are reaching to a cell in 2 steps, you will update the parent. But if you are reaching to the same cell at 8 steps, you won't update the parent, right? Because this is not the correct parent. This parent is not the correct parent. This parent was the correct parent. So that is what you are actually doing. So I hope all of you understood it. Thank you.